Hello, my friends, and welcome to another fabulous episode of the AI Show. My name is Seth Juarez. Let me put my corner up here so everybody knows it's the AI Show. I am excited to be here. Welcome, welcome, welcome. Where's everybody coming from? I see there's a couple of people that have tuned in. Welcome. Jose Silva. Jose Silva. Trying to do some cool audio effects here. Let me do that. Jay McCormick. Hold on, let me make it better. Jay McCormick. I can't hear myself. You mean the art of the backboard doesn't inspire? The art on the backboard doesn't inspire AI? This is all AI generated. At least the AI of my children. McLean? Is it McLean or McLean? It's got to be McLean. Virginia. Welcome, my friend. Sharafuddin. Hello, my friend. Ivana. Happy Friday. 10% battery. No bueno. Jenny Skew, number 7, Seth. That's right. Señor Juarez, aquí estamos. Today it's all project all the time, so I'm excited about that myself. And I thought I'd do something because I was. The goal is to not work on these things whilst you're not watching, but I had to because I had to give a talk on Tuesday, and then another one on Thursday, and I was like, this code we wrote together is so nice. I should use it, and I made some changes. So I'm going to go through with the changes I've made. And I think we'll just move this AI spot to the cloud. We're going to shift gears because it's not that I don't like JavaScript. It's that JavaScript doesn't like me. And man, I'm such a slacker. I forgot to turn on my background music thing. You're probably looking at me like, Seth, there's background music right now, but it's not the same. Like, I do things weirdly. Let me make sure everything's turned off here. Okay, good. Sammy! Oh my gosh. How you doing, Sammy? I am well. Eli from Denver. Welcome, my friend. And if I'm looking over, it's because my computer screen is here. So, apologies. JavaScript apes everybody. Any news on Blazor with Onyx? That's a good question. I have no news because if I'm being completely honest, the things I work on the most are AI platform type stuff. I'll show you today. JavaScript FIAs not love a lot of us. That's right. It doesn't. But TypeScript loves, yes. TypeScript is fantastic. I love it, Mathail. All right, what's the program I use here for this? Oh, there it is. I hadn't turned on my background music thing yet, so let me do that now. But yeah, today I'm going to show. I think today I'm going to spend more time. Sorry, I got to go to the mic. Today I'm going to spend more time talking about infrastructure for AI and ML ops. If that's okay. Oh, this thing is not opening. What happens, friends, when you don't turn on the background music. Repeat all. Oh, repeat all. There we go. Okay. So this is going. This will be ready for me. All right. Hopefully the background music now is working. I don't hear it. Oh, it's not working. I gotta push play. I thought today we'd spend some more time talking about AI infrastructure. Something to test on Blazor AI site. Fun story. I was there when it was NDC Oslo. Mr. Sanderson, who lives in the UK, I think still, did a demo of Blazor. Like it wasn't. I don't think it was called Blazor back then. It was what's that thing called when you run native stuff in the browser? What's that called? I forget what it's called. WebAssembly. That's it. And then he's like a bit confused. Why? Because Blazor, I would have to use JavaScript either way, right? Because I don't know if there's Blazor bindings for Onyx.js, and so that's what shuffle all. WebAssembly, that's it. And I was like, this is cool. But again, like if you like doing that stuff, that's awesome. But to me, it felt like another layer of abstraction if I could just use JavaScript, unless Blazor's faster. I remember I had this conversation with Rocky Lotka, if you know who he is. He's the guy that did what was the thing he did? He did like a really cool framework for C#, and he explained to me, because I didn't understand it, like, and he was like, the other reason, Seth, is because we can share code, because like if you're writing DTO types, data transfer object types, to go from like an API over, you'd have to rehydrate it into TypeScript objects, etc. A CSLA, that's right, Eli. Really good dude, by the way, Rocky, super good dude. And he's like, yeah, I can share code. And I was like, oh, okay, I can see that. But for me, there's a larger ecosystem in JavaScript already that's not on Blazor that I could just readily use, and they've already solved a lot of the problems. So that's why I learned React. But yeah. Okay, so let's do this. Let's talk about what we're doing today. These are good questions, by the way. And like I said, the cool thing about Blazor is that if you love it, you get to use it. I think it's great. Let's turn this on. Well, my background is ugly today. What is going on with you, Seth? Here we go. This is the wrong background. We want this background. Boom. There you go. You can use whatever you like. And that's the great thing. Okay, so today, what I'm going to do is I'm going to show you the changes I made to the AI code. And we're going to go through it together. And we'll run it again. Number two, I'm going to show you. Let's here. We're gonna move the AI building to the cloud. So we're gonna start to do some ML ops here. Just because I need a timeout. I feel like I need a timeout from JavaScript. Because last time I was like, okay, I'm passing an array to an API, and now I need to reshape the tensor. How do I even do that in JavaScript? And I even considered between us girls kind of thing. Should I move my API from Node to Python? Because if I did that, I would write this so fast, just because I already know how to do. I capitalize the T, and it's going to bother me. Python. Okay, I did that. This is terrible. I'm such a terrible writer. Python. You know what I'm talking about, right? So when we're in here, remember there's an API, and we got this get message or this post image thing, and we got it to the point where it was getting the actual array of numbers. But I just didn't know if I wanted to. I wonder if I can go to this definition. There you go. I'm wondering if it has reshape abilities. And how do you work with tensors? And this stuff is so new that there's not a lot of documentation. So I suspect y'all would just watch me be like frustrated and stuff. Which is cool too. I mean, frustrated Seth is super funny. Yes, Eli, Mo frameworks, Mo options. Indeed. Indeed. Keep it simple. Yes, indeed. But that's the thing. Like, if you enjoy if you want to use Blazor, I think that's glorious. You use what makes you happy and pays your bills. I'm a fan of that. But anyways, I was thinking like this stuff. I mean, I wonder how hard it would be to change the API to Python, or if that's even possible. So maybe we'll spend a minute investigating that. But then I want to show you, I made some changes. I added all this cloud stuff. And you're like, why did you do it? This stuff takes a long time because you have to get your environments right, etc. We'll talk about it. So going back to the things that we're doing today, changes in AI code. We'll talk about that. I'll show you how to move stuff from AI to the cloud. We'll maybe, if we have time, I think we'll have time. Maybe what we'll do is we'll try this. Try it, our API with Node. And then if we get really angry, we'll just be like, you know what? Let's investigate this. Okay. So DF Meta is saying, I got lost. Why do you need to if you're doing inference in React? So I'm kind of not. I wanted to do inference in the API first, just to, and then work on, because I'm talking to the Onyx people on Monday to see if they'll come on next Friday to be like, hey, look, here's how you slim down your Onyx model and run it in the browser. But right now the model's too big. So I thought I would just get it to work in Node first, hoping that it'd be similar in React. So that's a good question. So, yeah, because the model right now, you remember, is big-ish. Let's see how big-ish it is. By the way, today I went to dark mode. Dark mode in Windows. So this is huge, right? This is. It's 100 megabytes, and I remember Burke. Remember, he came on and helped us with the static site. It was like 100 megabytes. So yes, okay, yes. Try and start thinking of who to do. I already have 2 people, and then I have some other people that I'm hoping that they're saying that I'm not using the command line right, and they're like, you should use something else. I'm excited to have them explain to me how to make it better. Yeah, Seth on dark mode. Dark mode. Dark mode. Yeah. Okay. And like I said, as I'm going, y'all need to stop me for questions and stuff. I think I'm done with this thing today. I'll just set it aside if I use it later. That'd be great. But that's what we're going to do today. We'll start with the changes and go from there. Okay, so for those wondering, I did make a couple of changes to the AI code. And I know y'all weren't here for that. But again, I had to give a talk at Codepalooza. And so I used this code because we so lovingly created it. So let's go to the AI part. The first thing we did is... let me show you what I did. Conda, activate, torch. Is this too small? This feels like it's too small. Boop. Better. I think that's the command. So I basically upgraded PyTorch and PyTorch Lightning. So let's do this. Pip list grep torch So that's the first thing I did. PyTorch Lightning now is at 142. Doop. Let's zoom in here so y'all can see what I did. So the first thing I did is I upgraded PyTorch to now 1.9.0 with CUDA 11.1. CUDA 11.1 is running. It's nice. Torch Vision. So this is the most important one. And then the second most important one is I upgraded PyTorch Lightning 142, which unfortunately is causing warnings. Yes. So that's what I did for that. And then I cleaned up anything that's different. So let me go and see if I can find the diffs here. GitHub. AI advocate Rochambeau. Let's look at the commit that we just did last time. Let's see what the difference is in code. Oh yeah. These are just some settings. I fixed some of the way you run stuff. You can see that in the task. Because remember how we changed the folder structure? By the way, question. Any ideas on next release .NET 6 in AI solution for Blazor on ASP.NET? I do not know, unfortunately. I know who to ask. I mean, shoot, I can ask somebody. Let me write this down. Ask somebody. Get my fancy pen out. Old school. .NET 6. AI solution for Blazor. ASP.NET core features. Yes, I'll ask. I don't know, to be honest. Okay, so notice that launch.json is the same. The other thing that I changed is in the trainer, my model was kind of not working really well. The one that we thought worked well didn't work well. I changed the early stopping to measure loss instead of accuracy. And I said 10 to the minus 4 with a patience of 5. So I changed to that. And then I added a learning rate monitor for kicks and giggles because we have a learning rate scheduler. The other thing I did is you can see right here, I just made this clearer because this was always like, well, what the heck is he doing here? Basically, we're taking the pixels of the picture and we're fixing the mean and standard deviation. And then I also changed the output file to something not so squirrely. And then I moved it over to a ResNet 34 as the base model. I was using a ResNet 18 and it just wasn't doing it for me. And then I added some Azure isms, but not much. You can see there's no Azure things in here. But basically I had to deploy this and I do a lot more logging, as you can see. I also do, this thing is a definition script. Oh, what's the tech stack? We'll get to that. Eli, what's the tech stack? We're using Python and PyTorch and PyTorch Lightning. And yeah. And that's it. That's basically the majority of the changes, as well as some of the stuff we did on the website that you all saw me do this. I just hadn't checked it in. So those are the changes. But now I want to get into it a little bit more granular. CLS here. It looks a little pachucho, as we would say in Spain. Okay. So let's close all the things and let's get into what we're doing. And then let's see if we can't get it to work in the cloud, my dear friends. So what we have here is we have a problem where I want to take some images of me doing like nothing. Just me hanging out. Me doing paper. Me doing rock. What's funny is I have this whole board of sound effects, and I just use my mouth sound effects. And then scissors. Doop. And what we're doing is we're taking those pictures as our data, and we're pushing it into PyTorch Lightning to produce our model. That's what we're doing. PyTorch Lightning is a extensibility framework built on top of PyTorch. So that's what's going on there. You can see here is my data stuff. It's not a lot. You're looking at this, you're like, that's all the code. Yes, that's it. We basically do a transform and a normalization of the images as they come in. The image folder will retrieve the classes for us by folder. And then I do my random split, and then I do a training and a validation data loader. Happy to get into PyTorch stuff. But if you're like, I don't know a lot about PyTorch and I want to learn it, maybe one of these days we can actually go through this. But we have the PyTorch fundamentals learning path. I'm going to Google with Bing. Look at that. Let's go there. Boom. You can totally do this. I actually wrote this first one. Yeah. So you can learn about that. And what PyTorch Lightning does is it makes it even more simplified. I forgot to load up Learn TV Pubble. So Learn. I want to make sure if you're saying hi to me on Learn TV, that I got that there. So AI show live. Let's make sure that the audio is turned on. Nice. Okay. So if you Learn TV, say hi. But this is how you can do all this stuff. You can totally learn PyTorch. It's super nice. Oh, look, it's me. Hey, yo. Nice. So this is the data. The model is here. You can see there's not a lot of code to look at, but you can see that I'm using a transfer layer of a ResNet 34, 2 linear fully connected layers, and then I'm doing some ReLU-fying on the outputs of these fully connected layers. I don't know if I need to do a ReLU on this. No, I do. And then a softmax at the end to pretend that these are percentages. And you can see that basically when I run these things, I run it, get a loss, and then do some predicciones. This is the accuracy. This is a training step, validation step. This is the optimizer I'm using. I'm using stochastic gradient descent. Although, maybe this is a problem too. Maybe I should be using Atom. What's my loss function? Oh, yeah, cross entropy loss is good. What else is there? There's like 2 entropies. Let's do binary cross entropy. That's probably going to be better. Maybe that's why my model sucks. Let's try doing an Atom optimizer. Maybe that's why my model's been kind of stinky. Let's run it. By the way, if you're looking at what I'm doing, you're like, I have no idea what the heck Seth is doing. Let me know. And Blazor.ai. I want to see this. Hold on. Danny's saying, check Blazor.ai site to see what it. Let's look at it. Let's look at it together. This is supposed to repeat forever. Repeat all. There we go. Got real quiet in here. Blazor. What did you say? Blazor.ai. Is there a Blazor.ai? Let's see. You better not be sending me to bad websites. Yanni. If you go with generic algorithm in your browser, don't worry, you can't break it, we promise. Oh, hey, nice. TSP. NP complete. Oh, hey, this is nice. But it's only a genetic algorithm. Blazor size. Component library. What is this? Blazor has a component library built on top of Blazor with support for systems like Bootstrap, blah, blah, blah. Well, Blazor has come a long way. I will accept your cookies because it's Friday. Interesting. By the way, for those that don't know, I wrote a long time ago .NET framework. Look, it's not even secure anymore. This would very well work in Blazor because it's all pure .NET. And I have a naive Bayes neural network. It's just not fast, right? Because I have to use I made my own like matrix, and vector, and they're all doubles. This might work in Blazor. I don't know if anyone wants to let me know. Take it, kind of thing. Okay. All right. So Python trainer config.yaml. Get ready for my GPU to be like. Here we go. Is PyTorch similar to Tensor? So a great question. So you probably mean TensorFlow. So the answer is yes. Basically, PyTorch and TensorFlow are machine learning libraries that are really good at creating like structured models. Wow, why is it saying my internet is slow? I'm plugged into the connection is fairly good. Not even on Wi-Fi. Uh-oh. Let's see what's going on here. Something broke. Let's see here. Using the target size that is different from the input size is deprecated. It might be, I might have to be a little denser. BCE loss. Let me not do Atom and then see if SGD fixes it, but that should really make a difference. Let's see what's happening here. Oh no, it's on the cross entropy bit. That's going to break too. Let's go to definition here. Oh, so they're not the same shape. Okay, we can fix that. Because I think binary cross entropy is going to be better for us because that's what I've used before. So let's stick with Atom here. Forward training. Where are you? Figure out that we'll go back to Atom because that wasn't the problem. Maybe this was something wrong with this the whole time. So Y hat, and let's do this. Let's actually, and this is the really cool part about Visual Studio Code, is that I can actually try to run it. So let's go over here, and we're going to run the PyTorch Lightning Trainer and set a breakpoint. And this is the cool thing about Visual Studio Code and PyTorch, and that you can I can debug this stuff and see where the shape issues are. I'm guessing that it's this thing that I want here to be put in here. Yeah, I don't care. F5. Oh, no. Why isn't it letting me do this? Dang it. Let me try one more time. It might be that I'm using too much GPU-ness. We'll see the error again. CD Rochambeau AI. Conda, run this. Torch, yes, use it, blah, blah, blah. We're using the right environment. Trainer config, yes, yes, yes. You are missing, blah, blah, blah. Finding the CUDA device. Model. Okay, there we are. So it's expecting these things to be the same size. And of course, they're not. Okay. So let's go over here. Okay. Do you see the problem? I don't even know how this was working before, to be completely honest. It's probably why our model stinks now that I'm looking at it. And we never caught this. So embarrassing. So embarrassing. That was my inner child screaming. So, for those that are looking at this and saying, I don't know what the heck he's talking about, let me explain. So what happens is we give the computer some data, and it goes through this loop of trying to optimize this internal model's numbers. It uses linear algebra and calculus. Right? There is a model function, f of x, that produces a y that's supposed to be the right answer. Right? What we do is we make this function called the loss function that takes f of x and the right value and the right answer, and it measures how bad we are at it. If the answer is 0, then we got it exactly right every time. If the answer is greater than 0, that's bad. So basically, machine learning is taking this loss function, f of x comma y, which is the right answer in our model, and it's trying to minimize it with respect to the parameterizations of f of x, which are the numbers, you know? And so to do that, you all remember, we take the gradient of this function, loss function, with respect to the parameterizations of f of x. I'm going to write this again because it feels like I just said something that's actually feels more complicated. So I'm going to go full whiteboard again. We're going to go full whiteboard while it's on a breakpoint. So let me say this again. Machine learning is the process of writing a function that learns itself. This function gives the input x, like the picture of me doing rock, paper, scissors, and out comes an answer, which belongs to the set of rock, paper, scissors, and none. That's what this function that we're trying to machine learn does. The loss function, because this is the x value, we also have available during training the y value, which is the right answer. So basically, the loss function is a function that takes f of x, the value that produces the actual model, the output, the answer y, and this tells us how good we are at it. If the answer is 0, right, that means that the difference between what we predict and what the right answer is 0, which means there's no difference. We're getting it right every time. If it's greater than 0, that means that we're sometimes not getting the right answer, which means that sometimes this model is, well, sucky. That's why in my brain, my 12-year-old self says the loss function is actually
the sucky function. This is the sucky function.
Right here. This is how bad the model is. So, as you know, if you've ever taken a calculus class, calculus is all about finding where things change or don't change. So this function is ostensibly some curve, right? This loss function, right? And what we want to do is we want to find the parameterizations of f of x that make this the minimum possible. And so to do that, you take the first derivative, set it equal to 0, find the loss. And you're basically, the loop is traveling over this function to find the exact loss. So basically now, to be completely sticky, we're doing the gradient of the loss function with respect to the parameterizations of f of x. Wow, that was terrible. I'm gonna write this bigger. We're taking the gradient, which is the same thing as a derivative, of the loss function with respect to the parameterizations of the model function, of the loss function f of x, comma y. This loss function you can pick whenever you want, and there's loss functions that are better than other ones. The loss function that I wanted to choose was binary cross entropy. For some reason, I was getting a sizing error, and I just said, oh, heck with it. I'll just do cross entropy, which was wrong because there was still a sizing error. So what's happening here is that we're getting out a tensor y hat. Let's see where the shape is. Let's just go to the debug console. So we'll look at y hat dot shape. I think that works. And the shape of y hat is 32 by 4. And I'm guessing that the shape of y is 32. And you're like, what the heck are these numbers? I'm so glad you asked. And we're on a 2-hour live stream. When we configured this thing, we said that for each step in the loop, our batch size is going to be 32 images that we're working with. So when we go back to this goodness, you're seeing that the shape of y, which is the right answer, is 32 because we're doing 32 at a time. But the answer that's being produced by this thing happens to be 32 by 4. And you're saying, well, what the heck, Seth? Why is your model function producing 32 by 4? I'm glad you asked. Let me go over here. Because it turns out that the model function that we built to be very sticky does a softmax over the number of classes in the output. And you're saying, what does that mean? Well, it means that a huge picture comes in, a tensor, and then it goes through this washing machine of numbers, and out comes this vector of size 4, right, with numbers in it, and the number tells us the index, either 0, 1, 2, or 3, of the right answer. Right? And so we do the max index. The problem that we have is that we have 32 of these, hence that's why we have a 32 by 4 tensor. Right? Let me show you some other goodness here as we go through. By the way, this is all a machine learning, like getting the wrong index. What we want to do is we want to get this vector, right, which is basically a huge matrix over here with numbers like 0.2, 0.1, 0.7, 0.7. Oh, I already did it. I already did 0.001, right? Because there's going to be 32 of those. What we want to do is we want to take the max index of this thing, and output a vector that says, looks like it was position 2, 0, 1, 2, 2, 1, 0, 1, all the way 32 times. And then this is a vector of size 32, which corresponds to the right answer. Or the other thing we can do, and y'all, we can decide together, is because this thing is like this, right? This is picture number 1 for the batch, 0.2, 0.1, 0.7, 0.0. What we can do is we can change this like 2 to a 0, 0, 1, 0. Or like a 1, 0, 1, 0, etc. And then pass this in. So which one should we do? Am I making any sense? Someone stop me. Be like, you didn't explain this right. Look, and if you don't understand this, don't be like, oh, I'm dumb, I don't understand this. Just be like, oh, Seth didn't explain this right. That's actually more accurate. Right? So Any questions about what we're trying to fix and why it's not working? Anybody there? Is it just me? Yellow? Where's everybody? Or is it a Matrix? Yes, Matrix. Oh, I forgot to turn my In the Cave voice off. Yes, it is indeed in the Matrix. So we have two options. I think I want to opt for this one, if I'm being honest. Where did Y become 32? Great question. Good question. Is this how you learn Kung Fu? Yes. Yes. AI Kung Fu. When did Y become 32? Great. So let's go back. Let's go to Jay's question, which is great because I think the problem is it's like I'm throwing a bunch of stuff at you. So basically, this 32 number means that for each batch that comes in, right, our batch is giving you two tensors. It's giving you the X value, which is the image, right? And the X value is just 3 by 224 by 224. Well, I'll show you. It's going to be 32 by 3 by 224 by 224, right? And I notice I did that without telling you what's going on. So if it was 1, this would represent one image. Channels RGB, height, width. Those are the pixels, right? The reason why there's 3, it's not just 224 by 224, is because each pixel has 3 numbers, red, green, and blue. This says how many pictures we're passing in at the same time, because the loop that goes through and does the optimization that I was talking about batches a bunch of images at the same time and runs the loss function, runs the model function, runs the loss function, and optimizes the parameters per batch. Because we did it for every single picture, take forever. And so we batch them together, right? The reason why Y is 32 is because Y, here, I'll just show you why. Y happens to be the right answer, right? This is the index for paper, for example. This is the index for rock, scissors, rock, none, right? So the reason why Y became 32 is because there's 32 answers that correspond to the 32 pictures in the batch. Does this work? Should we do this in my robot voice? The computer wants everything to be in numbers, so we oblige it. Yes. Okay, cool. And what's happening is the binary cross entropy function for loss expects the shapes of these things to be the same. To be completely clear, cross entropy did too. I was just using it wrong. So we have an option now. Because the answer comes out in this shape, right, which is we just got to pull the max index for each one. Remember, and there's 32 of them. We have the option of max indexing and then doing cross entropy, or changing the Y to a 32 by 4 matrix. And I don't remember how to do that. PyTorch.org. PyTorch. Yes. Yes. The answer is 32 as a batch size. Yes, that is the right answer. Okay. Tutorials here. How do I change that over? Quick start. Shape of Y, shape of X. Am I using binary? Are they using binary cross entropy here? It's a loss function. Loss function. Oh, it's just cross entropy. Oh, is this wrong too? Who wrote this garbage? Yes. The question from Jose Silva: did you change the learning architecture? Yes, I changed it to ResNet 32 with a fully connected 1000 to 256, 256 to 4. I probably didn't have to change it. I was probably using the wrong Y value. Oops, I pushed the wrong button. Let's go back here. Quick start. Let's see what I do with the Y here, because fashion MNIST is similar. Batch size 64. Creating the model. Linear ReLU stack. Oh yeah, I don't like this. I might pull request change this. We're using cross entropy loss again. Y to divide. See, this is wrong. This is wrong. Let's go see github.com. Seth Juarez. Well, that's embarrassing. I might do a pull request to fix that, to be honest. Let's see how I fixed this before. Batch is a function. Let's go to it. Line 18. You know what I do? Oh my goodness. I think I do this in the data loader. This is also wrong. What the heck, Seth? The question is, why did I change it? It's because it wasn't giving me accurate. It wasn't really giving me accurate results, and so I thought I needed deeper neural network. Now I suspect it's because I wasn't counting. I wasn't doing the thing right. So let's go to a rearrange. No, I know what I can look at. Deep learning with PyTorch. Ask Seth. Past Seth. It's going to fix this. By the way, this is how I train people in PyTorch, by the way. It's super handy, but I'm not finding the thing that I want. Utils.square. Yep, look at that. Yep, look at that. Yep, that's how you fix it. Okay, let's do it. Let's do a little try here and fix this out, because I might be able to fix this in the data set as opposed to, and then this is going to be 4 instead, and this is going to be 32. And yes, this is right. So take a look at what I'm doing. This tensor is now going to become the right size. Oof. There you go. I just made that change. And so now, look at this. 2 becomes 0, 0, 1, 0. Okay. I need to fix this. I need to fix this in the, yeah. So Jay's saying change the Y to 32 by 4. And that's what I just did. This error is because this tensor Y lives on the GPU. And this tensor right here that we just created lives on the CPU. So I had to move it to the right device. This creates a new tensor and then this scatters it in the right place. Scatters a 1 in the right place. You can see that right there. So what we have to do is we can either fix this here, or fix it here, which is what I think we should be doing. And there's a way to do that directly in the transform. So I don't have to... Where did I do this before? I think under MNIST. Let's take a look at digits. Because there might be a way to just do a transform. There it is. That's it. Oh! This is going to do it. Let's fix it. That's why my model was super stinky. We can stop here. So this is the transform. Wait a minute. Wait a minute. So we have a transform, and then we need a target transform. Self dot target transform equals transforms dot compose. Doop, doop, doop. No, not that. Jose's like, great, Leon, let's do Maui and Ski Sharp. Yes, maybe we'll do that one day. Here we go. I'll just copy this. Oof. Torch is not defined. We'll see about that. Okay. Okay. And this isn't this. It's going to be self.batch size. Right? Yeah. Yep. This will do it. This will do it. Now, when we do this again, it should be all the right size. So let's F5 this goodness and then see what happens. Float. That's a good question, Jay. I don't know. Here we go. Here we go. Here we go. We're coming to the compute side. Boom. Let's go to yhat.shape. And we're going to say y.shape. Yhat.shape. 32 by 4. Boop. Y.shape. No! Oh, I'm an idiot. Of course it didn't work. Derf. I defined it, but didn't do it. Is there a target transform? Yep, there it is. That's why. That's why it no work. We did not tell it to do the right thing. Oh, embarrassing, you know? Like you think you know a thing, but you don't. You don't. Oh, here we go. Here we go. I didn't do a target transform because I'm a goofball. Okay, here we go. Okoli dokoli, stop here, stop. Stop, okay? Now let's just say y hat dot shape 30 by 4. Y dot shape. Oh no. I did it wrong. This is why. So embarrassing. It's actually a number of classes here. Oopsie. Oopsie. Yes. Go do the Cosmos DB things. To the cloud. Sharafine, why don't you use GitHub Copilot? I think if I used AI to write AI, the internet would break. I don't have access to GitHub Copilot because I'm not important. So that's the real reason. All right. I think this is the right way now. Oopsie. That was embarrassing. In fact, you even remember when oh, it's not there anymore. I even put the 4 in there instead of a 3. Here we go. So didn't like this. What did I put in there before here? No, there was something I did that was smarter than this. On the square. Self. Not batch size. Comma self. Oops. Okay. Just for reference, you can see here the batch size, the class size. Batch size, class size. Here. How do I scroll over? Where's the scroll bar? I mean, come on. Where's your scrolly? There it is. And inline scatter. Inline scatter. Yeah. Huh. I think this will work. This is another way of doing it. Maybe I'll change it to this, but I don't want to. By the way, whenever you see an underline like this, it's inlining into the same matrix vector, right? It's not making a new vector or a matrix, I guess in this case. Hey, stop. One more time. I've been doing this wrong the whole time. What is going on? Oh, derf. Like this. The other thing is that now this changes too. Okay. Okay. Let's see if this fixes it. And if it doesn't, then I'm using the wrong call. We're going to do this. It's going to work. Oh, gosh dang it. Okay, let me see what I did here, because this one seems to be, this one worked. Let's see what the difference is here between these two things. Okay. Let's try this. I don't know why this would work better, but it looked right when we did it in the debug view. So let's try this. Here we go. Oh! Argument size must be a tuple event, but found an element of type list at position 2. What's in there? Oh my gosh, you gotta be kidding me. Oh, no wonder. Oh, that was dumb. Oh, jeez. Oh my goodness, that was not very intelligent. Oh, jeez. Oopsie. Yeah, this is what AI debugging is all about. Making sure your things are the right size. I bet our model gets much smarter now because of this. No! Int object has no attribute. Oh, of course, that makes sense. That makes sense. I know why that's doing that. That makes sense. I did the wrong thing again. Idiots. This is like code I wrote, you know, that I don't even remember how it works. Here we go. Torch.tensor y value 1. This is why this has to be this way. Scatter on this. Oakley dokley. Now let's try it. Let's do it. This is called a one-hot encoding, incidentally, for those that are wondering. We're trying to one-hot encode the answer space to match the input space. And the reason why this is actually really good is because the binary cross entropy will start to measure the difference in the whole thing. Oh, come on. Index tensor must have said self.tensor. Why isn't this working? Come on, Seth. I know why. I know why. I know why. Okay. Okay, here we go. This is going to be the one. I feel it in my bones. Here we go. Boom! Let's measure the shapes. Y hat, we know the shape because that's the one we made. And then Y. Booyah! Now let's go here. Predictions. There you go. The truth. The accuracy. Oh, it's working. Man, that accuracy number is bad. Here we go. Let's see if it improves. Man, that loss is high. Here we go. Here we go. Epoch 3. Epoch 4. Is this not getting any smarter? Oh, man. This accuracy is horrid. It's not right. It was just terrible. Let's move over to Atom Optimizer. Oh, it is an Atom Optimizer. Gosh, that was terrible. We did the. All right. Let's see what this does. Here we go. Oh, the accuracy. Oh, wow. Maybe I didn't parameterize my Atom Optimizer well enough. Let's look at the accuracy now. We're already at 95. 95 min delta. Validation loss improved by 0.050. I'm feeling better about this, friends. Yeah, you're right. Now look at this. Look at this, Jenny Skew. Yeah, he's saying not even above 50. I know. But now, I mean, the loss is still improving. And the cool thing is that, and this is the cool part. The cool part is that this thing will keep going if the min delta is, because it's going to find a minimum and the learning rate is going to slow down auto-magically. This is great. This is awesome. Look at this. Is it getting smarter? Yeah. I mean, it's still improving. That loss is beautiful. Look at that. The loss before was like 45 or some craziness like that. But now it's like less than it's 0.0831. I wonder how long this will go for. All right, so for those that are joining, I basically fixed a problem with the way we're computing the loss. The loss wasn't even matching, and so I don't even know how I don't even know how this even worked before. So this is clearly much better. From Roman. CUDA, I'm using CUDA. What am I using? Here, let me open a new terminal. We'll do it here. I don't remember. I'll ask my Python packages. By the way, this is a question I'm answering. Conda activate torch pip list will grep over torch. .11, but I don't know. Let's see here. So that's that. Let me look at my drivers here. You know what I can do? I can actually go into my computer. Load, please. I don't know. I'm using CUDA 11.1. Let me just. That doesn't tell me it. I'm using CUDA 11.1. And then CUDA and then what is this? Sorry. .11.1, but I don't know. I think it's. I'm not sure. I'm using for sure 11.1 there. Oh yeah, that's right. That's right. Thanks, Ruben. NVCC. Good call. Absolutely. By the way, thanks. I totally forgot about that command. MVCC version. There we go. 11.1. I sneezed. There you go. Thank you. Totally forgot about that. Okay, so let's go back. This should be done. And let's do a scoring run on this. Yeah, now it's getting them exactly right. Oh my gosh, look at that. Ugh. This is so much better. So much better. I'm so glad we found that error. And it's just been lurking in there We never fixed it. Seth? Yeah, I mean, gosh, that was embarrassing. Yeah, this is much better. Beyond anything else. But you can see basically we did binary cross entropy. There was a misalignment in the shapes of these vectors, and we fixed it. We fixed it here by having a target transform and doing a scattering on the load. That way we don't have to, like, as it loads, it'll put everything in the right spot, and it'll load per batch, which is super efficient. So nice. Now we want to make this work in the cloud. So, because I need to submit this experiment in the cloud. Let me show you how we do that. That way I can start saving these things. If you've never seen this before, this is Azure Machine Learning. And the nice thing about I don't have a history of everything I've run. It's kind of a bummer. So this is the infrastructure part. I already set up a compute environment to run these things in. You want to see what I called it? Yeah, wizard! You have to upload your data, so let's do that. Experiments. All right, so let's do this. Explorer, storage, Explorer. There we go. What we are going to do is upload our stuff, make a data set so that the cloud can access this stuff. Vamonos! And hopefully we get this done in the next 40. We can do this. We can do this, friends. We can do this. So there's where I store all my data sets for machine learning. Oh, Edward, feels like we aren't getting your best today. Edward! Feel called out. It's gloomy here today. It's first day without sun. I had to take extra vitamin D. Thank you. All right, so this is a blob container. We have examples. Experiments is where I upload my experiments. So let's make a new folder here. New folder, Rochambeau. Rochambeau, okay. And let's just upload our pictures. So let's reveal this in File Explorer. File Explorer. And there's our data. There's our data. Let's go to the, is it images? Yeah. What's raw? I don't remember what raw is. Oh, wow. This looks better. What? Why? Let's go to the raw here, and let's go to not options. Show properties. Propiedades. How many files are there? 577 in 4 folders. What about this? Properties. This has less files. I'm just going to upload the raw ones. So we'll take this and we'll move this. Okay. Boop. So we're uploading my pictures to blob storage here so that we can run this in the cloud. Now, here's the thing. The thing I'm excited about this time is that we're going to be able to run this all in the cloud and keep track of this, if I make improvements. Because I don't even think I need a ResNet 34 anymore, to be honest. I mean, a ResNet 18 might work. Yeah. Are we done? Is this working? There we are. None, rock, paper, scissors. Fantastic. Fantastico. Then we'll go over here and we'll create a new data set. So we'll create a new data set from data store. because I just uploaded them to the examples. And we'll call this Rochambeau. This is a file data set. Next, we're going to use experiments, and we're going to browse to Rochambeau. Include files in subfolder. Save. Next. Create. So there you go. We basically created a in the cloud. Let's see if it worked. We basically created a place to have all our files to do training. Pretty excited about that. Let's see if it worked. Hey, yo, there's me. Is it another one? Another me. Look, we're sitting exactly the same. Let's see if I can replicate. Did it look the same? What? Okay. All right. So we got this is all sorted. The next thing we do is we need to define an environment. I already defined an environment that runs PyTorch Lightning stuff because I do it all the time. You can see it has a parent image. And then it has like the things that we need, like this stuff, PyTorch Lightning, CUDA toolkit. Now we just need to run the experiment in the cloud. And to do that, we have here this job thing. And the data we want to use is, let's see what we got here. Oh no, why isn't it loading the right thing? Let me take a look here. Wait, what is this? Is this running? Okay. So let me make sure I got the right data set here. Rochambeau. Yes. Refresh. We go over here and make sure it can see it. By the way, you can. This is all mapped to Visual Studio Code here, which is super nice. But I think it lost connections to stuff, so I'll restart it here. What a bummer! All right, here we go. Here we go. Now we're gonna get this machine learning, and then if I control space, I should see the right thing. I gotta wait for things to load. Loading. Here we go. Here we go. Everything's starting. It's all working. Yes. Loading. There it is. Rochambeau number 1. And the cool thing about this is we don't really change. We'll change the name of this so that we can keep track of it. The cool thing about this is we really don't change like our call. The only thing we do is we change the outputs of the files. So for example, like remember before we kept running trainer config.yaml. Now all I need to say is the data dir comes from this, which is this thing right here. Someone is using a blender in my house. All right. What? Oh gosh, all right, I'll reload it. So basically what we're doing is I uploaded the data. I pointed this run to this data. And then I have to describe like what I want it to run. So I'm calling it this. The local path is one directory up. Do you recall? Because we're in here, so one directory up. This thing tells it not to upload any of this stuff at all. So it's not. And then probably this one too. Azure ML outputs. We don't want any of those things to be uploaded. Or PyCache, for example. It's kind of like a git ignore that says don't upload any of this stuff because we just want these files. Yeah. Okay. So now that this is ready to go, I just need to run it. And hopefully, now that we have all this, it'll just show up in this area here. So let's run it right here. So right click, you just can do that or you can push on this. So I'm going to right click and do this. And in theory, what this will do is should run all this in the cloud, and it's actually going to be a better model. Way better model. In fact, let's try, once it does this one, let's try running it with a Resonate 18 and see if it's just as good. Because if it's just as good with a Resonate 18, it's going to be a smaller model. So we'll try both. And the cool thing is because this is working on a cluster of machines, it can do it at exactly the same time. I think. Look at that. There we go. It's running it. Now that it's doing that, oh, look at that. Nice. Nice. Now what I'm going to do is I'm going to change the model and go back to a Resonate 18. And let's run it again. Because why not? Cloud is big. We can run them all at the same time if we want to. All at the same time. There we go. Run another one. All at the same time. We got this. All right, let's see how it's doing. Oh, hey, yo, look at that. Look at this fine little graph. Looks like the accuracy is going up. Let's add some more charts. Let's look at the loss function. Loss. Oh, well, let's see what we got here. Validation loss. Save. I wonder if we have. Do I have more than validation loss? Do I have training loss? Let's see if I did. I not do training loss? Nope. Those are the only things I got. It's all good. Cancel. Oh no, we want to save this. Okay. Oh, see, now there's the other one running at the same time with a different model. Let's take a look at this thing right here. Looks good. Let's look at the metrics. Oh, see, look at that. It's like I'm smarter than you. Let's take a look at the loss. Yeah, loss is going to 0. Let's look at the outputs here. Yep, still running. And let me make sure the code is the one we wanted. So let's go to model here. Resonate 34 on this one. And on this one we have, it's queued. This one should have a snapshot as well. And this one should be Resonate 18. There it is, Resonate 18. I should have output that I was using a Resonate 18. I wonder if it does it on the other one. No, it doesn't. I should have added some, I should have added like a tag or something. Let me just add one right now. Model, Resonate 34. Just so that I can remember, you know, that's what happened there, Resonate 34. And then on this one, which is queued up, this one's a, let's add this one. Model, Resonate 18. Okay. And this one should, it's queued. Hopefully it'll load up soon when the machine starts because I have more than one machine. Wow, that is a beautiful looking graph. If I do say so myself. Yeah, very linear graph indeed. Accuracy goes from 76 to 1 and just stays there. I wonder if I can make this a logarithmic graph. Let's see here. Edit view. No, that's not what I want. Okay, so the first one's done. Cool. Let's try a different model type. Let's try a bunch of them. You know, because it's the cloud. We can do whatever we want. Let's see what a ResNet 50 does. ResNet 50. ResNet 50. We're running all of them. It's the cloud. We can run as many as we want at the same time. Looks like the number 2 is running. Refresh. What you got? What you got for us? How you doing? Very good. Model ResNet 18. You can see that is in there. That's a pretty good loss function. The accuracy is good. Number 3 is running now. Number trace is running. It's preparing. Let's try another one. I don't know. Because I want to know which one's the best one. What else should we run? Dots. Ooh, I know. MobileNet. I don't know if it's the same type of... I don't know. Let's try it. Shoot. If it fails, it fails. Now we're just running all the things because we can. Look at that. There's the other one. That's a ResNet 18. It looks like the ResNet 18 is doing similarly. And then the third one now, this is the ResNet 50. Let's go over here. I think this is the 50. Let's see what we got here. Model. ResNet 50. Details. ResNet 50. And then let's go back because there's a number 4 now. This is a MobileNet. Model. What kind of MobileNet was it? I don't remember. MobileNet V3 small. Okay. All right. Yeah, I mean, look at this. Smaller model. I think we're even getting a better loss with this smaller model. You know? I might just stick with a ResNet 18. We'll see if the MobileNet crashes. I didn't check for sizes or anything on the MobileNet. So, looks like 2 is done. Let's refresh this. Yeah, I mean, it got a better loss. Look at that. Look at that. The ResNet 18 has a better loss value. Same loss function. You know? Let's see what the ResNet 50 does. And sorry, I wanted to do this because I wanted to get, like, last week, like, when I was doing this, the model just was not doing the right thing. And I was like, what the heck? What's wrong with my model? And I didn't get a chance to, like, actually do science on it. You know what I'm saying? To know, is this the right model that I'm using? And it turns out that my code was even wrong, and we fixed that. And now we're taking a look at these things. Let's see what the next one looks like. There's a ResNet 50. The accuracy starts off pretty bad. Let's see if it gets smarter as it goes. This is cool, right? I mean, we basically are starting to run a bunch of stuff. We're doing some science. Look, run 3. Wow. Oh, it looks like this is run 4. This is MobileNet. Is this MobileNet? Yeah, this is MobileNet. Run 3 is just taking a long time per epoch. MobileNet's going. This is small MobileNet. Let's see here. It's like a horse race. It's like which horse are you going to bet on? MobileNet V small. Looks like everything is the same here. I don't know, which horse are y'all betting on? Oh, looks like the ResNet is taking a lot longer to do stuff. Oh, look at that. Looks like the loss is coming down. It's not as fast. By the way, for those of you looking at this, you're like, what the heck are these graphs even mean? So this is accuracy on the training data, right? This quickly goes to 1, but we don't want this to overfit. So we take a look at what the accuracy looks like on the validation data set, which is holdout data. And this is doing similar things, which is good. The loss function is as you recall, my child voice says,
the sucky function
tells us how bad we are at it. We want that to go to 0. So let's refresh here. Wow, ResNet, you are a slope. Oh, there's the ResNet. ResNet, no, I don't see the ResNet. Which one's the ResNet? ResNet's dark blue. So yeah, you can see ResNet has similar behavior to the other ones. Let's try a MobileNet V3 large. MobileNet V3 large. Why not? I mean, we got time. So let's load that up and go back. Very nice. Yeah, that ResNet is not getting us more performance for the amount of time it takes to run. Because I don't freeze the lower layers. They're not frozen, so it's actually optimizing the whole thing. It's not like a projection into, ResNet space. But you can see that yeah, there's number 5 running. And let's go back and not forget to add our label here so that we know which one's which. 4 is done. MobileNet's loss is not as good. And then what we can do is we can compare model size too. Like let's just say MobileNet is so tiny that we're okay with this loss. Great. Let's go here, refresh. Run number 5. Let's add you in. And let's tag you model large and see what we got going on over here. So yeah, I guess today we're spending more time on AI quality. And notice that that the experiment number 4, which is the MobileNet V3 small, went a lot longer because it kept improving itself until it stopped at about epoch 37, 38. It looks like the ResNet 34 stopped improving at epoch 10. So that's why these things stopped. And it's kind of a bummer. I wish I could reorganize the tags. Can I reorganize the tags? No. Oof. Why don't I do this? Let's see if I can fix the columns here. Edit columns. Min delta, experiment, node count. Mode? No, that's not it. Patience, weight decay, best score, restored. Stop, val accuracy, val count. Oh, why is it not in here? Model. No, it's just mode. Node count. I wonder how... No, I don't see it. I see learning rate and epochs, parent run ID, name. We got that. Node count. We don't need the run ID. Oh, I guess we don't have it. Favorite status submitted, duration, compute type, run type. That we got. What's the mode do? Oh, it's that's not useful. So we don't need the display name because that's just a GUID. Status, submitted time, duration, submitted by. I mean, fine. Let's save this and see what we got. Run type script. We don't need that. That doesn't add any information for us. Run type. We don't need that. But for sure, we don't need mode either. Edit mode. Take that off. Let's put the tags in there because that for sure we'll need. Very good. Save. And then we can see here, the tags are there. So that one's running. This one's MobileNet. This one's show all. Yeah, this is a ResNet 34. So let's select them all. Okay. So this one's running. Wow, the ResNet 50 is still. Oh, it just finished. Whew. Oh, cancel. We want to save this view real quick. Okay, so this is what science looks like. We have a couple of ideas. We see which ones are good. Number 5 is the MobileNet large. Number 4 is the MobileNet small. Number 3 is the ResNet. And yeah, it looks like they all... The MobileNet V3 small is not doing so well. I think the ResNet 18 gives us the most power for the smallest model. Let's take a look at how big the model sizes are. So let's go over here to the outputs and let's take a look at this model. I guess you can look at this. Doesn't tell us the size, but we can download it. I should probably output size. By the way, notice that I really didn't change any of our code. Did anybody notice that? I didn't really do any Azure isms. So I think I like the ResNet 18. So ResNet 18. So let's go over here to the ResNet 18. Although we should probably wait for the MobileNet V3 large, maybe. Let's go to this experiments here. Rochambeau. Run 5 is still going. Which run was the one we wanted? Run 2. Run 2. I think is the one we like the most because let's see if we can get this out to production in the next couple of minutes. I don't know if I'll be able to make it. So ResNet 18 is run 2. We finished with the best loss 3.361. This one's still going and it's pretty good little horse race there, right? Accuracy goes to 1, so there's really nothing. There's really nothing there, right? I mean. So let's do run 2. And let's pull that one down. So let's go ahead and download the outputs here. Let's do this. Let's go to AI and let's put them in there. And now what it's doing is it's basically downloading the outputs. They're all there. So, and let's go and look at those. Under Azure ML outputs, run number 2. Yeah, here they are. Model. There it is. That's what we want. So let's create a new model. Let's create a new model in Azure ML so that I can use that for later. So we'll call this one Rochambeau. Rochambeau, this is version 1. And this is our ResNet 18 that we thought was doing well. And this is run 2. Good. So let's create this resource. Yeah, and Yeah, there's a really short time for Resident 18 too, with less loss. So let's just do that. Looks like experiment number 5 is done. This loss got down to 57 on run 5. It finished, yeah. So it feels like the Resident 18 is giving us the most bang for our dollar. So we registered that model. Let's see here. Let's go to this thing. Is it still? Oh, it's still uploading it. It's uploading the model right now. Very good. So that should be ready to go. So let's go to refresh. There it is, Rochambeau Model 1. And then what we want to do is we want to take our scoring file, which is this thing, the thing we built before. It initialized the model, but instead, like when we run it locally, it basically looks in the outputs.model folder. But if it's running inside of Azure ML, it looks for an Azure ML environment for the model dir, and if it's in there, then it uses it. That's the only difference between the code. Everything else is exactly the same, except for this, which tells me the schema of what goes in and what goes out. And then that's it. I mean, everything else is just standard stuff that you would see. Okay, so let's deploy this now. Already created a deployment environment. Let's deploy this. We are going to call this one our Rochambeau endpoint. We don't want to use this model. We want to use. Oh, and I forgot. This is so new that it doesn't have autocomplete on this yet. Rochambeau, and then this is number 1. We want to use this, and then we want to use this scoring file. So let's run this here. Okay. So I just need to do this. I just need to do this. We're going to say cloud and then deploy. This is the command line tool for creating things. This takes about 9 minutes. But I want you to see it. All right, that was like a really fast, like, Azure ML thing. It's like, oh, let's make a cloud and let's figure out finally if this model is good or not. It wasn't. We had to fix some code that I made some mistakes on. We have here proof that we want to use a ResNet 18. We tried a ResNet 34, 18, 50, MobileNet v3 small, MobileNet v3 large. And then we create a couple of environments, to deploy these things. And now it's time to deploy this thing. Refresh. And you'll see here that it's just going to, again, this part takes about 9 minutes. Oh, sorry, probably 8 minutes. And the reason why is because it's making a container. It's creating a new deployment. And by the way, I went through any thoughts on like Azure ML as a platform? Like I wasn't trying to show you. I mean, I guess I was, but I really was more interested in making sure we had exactly the right model, and I wanted to make sure we had the right model once and for all before I start using it in the API. What are your thoughts? Any thoughts on what I just showed you in Azure ML? I'm curious. There's no thoughts on a Friday afternoon, Seth. Okay. There you go. Still working on this. This takes again, like it's deploying. Oh, by the way, this is a GPU machine. GPU, because only the best for our viewers. GPU. I'd asked for more quota because they're like, hey, Seth, you ran out of the ability to use GPUs. And I thought, like, what? Well, Seth, it turns out that you're not paying us for any of this stuff. Yeah, but I mean, I'm showing it to other people. Yeah, but we still have to. This isn't. You're not paying for this, so that's why we don't want you to use all of them because we have customers. Oh, okay, I get it. Yeah. Yeah, it is fast to use. The only thing that's not fast, Janny's Coo, and I want to warn you up front, is creating these environments sucks. It just takes a long time. Like, and if you make a single mistake, like you got to wait for the thing to rebuild. Thankfully for me, it took me 6 times to get this environment to work. It took me 3 times to get this one to work. But once it works, I don't think about it anymore. It's like if I like that environment, that's an environment that's for everybody to use. I don't ever have to think about it again. It's like, you know how you have to set up your machine the first time? That's it. And it was really fast. I mean, you notice that I just started shooting jobs at it, and it was like, okay, I'll do the work. And it did. We did 5 runs. The first one was 12:27. The last one was 12:38, and we spent what? Is that like 10 minutes running 5 different, very complex deep learning models? And we have a really fine little output graph that tells us, you know, oh, here's scientific proof that you want model number 2. All right, let's see how this thing is baking. Still baking. It's still a baking. Let's go over here. Let's see if there's no deployment logs currently. But it's working. It's provisioning. It's updating. Yeah. All right. I think the coolest thing for us friends was, by the way, I saved this all here. So for example, how to create environments, that's here. And then we're going to do some inferencing. You can do that with here. You can do that here. I'm just going to call it inline once it's done. I'll check these in, and you can all look at this stuff. And this AML ignore is nice, so that when I submit the data, the snapshot has exactly what we want. For example, here, run number 5 snapshot only has the files that we want. I guess we don't need the git ignore. But AML ignore, we have the init, right? We have the config.yaml to see everything that's going on, etc. You know, we might also, the other thing we could have done that I did not think about is we could also pass in a parameter that changes the actual. What's up? Do I want a sandwich? What? Yes. Oh my gosh. I have the best wife. She's comes in. She's like, "Do you want a sandwich?" I'm like, "Yes, I do." She's so nice. Oh my gosh, it's almost time to do the walk-off music. It's still going though. But yeah, that's what we did. We basically just did all this in the cloud. And the other thing that's cool is once Rochambeau really starts taking off and other people start using it, maybe we can get people to submit. We can get people to submit their own images and put it into this pipeline, and then just have this thing retrain all the time. And that's called ML Ops, and we'll get into that a little bit more. I know I wasn't. The goal wasn't to like show you this. The goal was really to make a good model, and this so happened to be the tool that I like to use, to be honest. But this is a really cool graph. We see all this going. And look, I'm stalling enough, okay? I've stalled enough. Help me out. Be done. Let's go to endpoints. And Rochambeau endpoint. Refresh. Oh, the scoring script is in there. Maybe the deployment log is in there. Not yet. No yet, but I did tell you it takes about 9 minutes. So it's not like I didn't warn y'all. Yeah. Sometimes you got to fix your model. People are like, I didn't know that we were going to have a 2-hour show on technical debt. That's just what you got. Because, like I said, I worked on this, and now I'm so glad we figured this out together. I worked on this on Tuesday, and then I had a talk on Thursday in Kentucky. And I was like, why is my model so garbagey? This is not a hard problem. And I was like, I got to figure this out before I move forward. And so I'm glad we did. We finally got it to work. It's not done. It's almost done. I'm glad we did, because now I'm very confident that our model is what we want. So that whenever we get the Onyx people to come on, maybe they'll help me quantize the model in such a way that makes it so that we can run it directly in the browser, as DF Meta was saying we should do, and then also getting it to run in the back end as well. And then also we have an endpoint now that I can just call from. I can just call from the thing, and then we can fix our endpoint to do the right thing. So let's see here. How we doing? Updating. Oh my gosh, it's time for the walk-off music. I think we're gonna make it. I might have timed this just right. Anybody have any cool weekend plans, by the way, just out of curiosity? Tomorrow I'm going to try to have, next week I'm going to try to have some special guests to help us make this work on the website. And maybe even some cool command line stuff with WSL. I'm talking to them. I said, hey, y'all want to come on the show and maybe tell me how I can do this better? And they said, you know what? We might be willing to do that. So, yeah. All right, what do we got? Are you done? Are we going to make it? Push. Are we going to make it? I hope so. But again, this is just deploying an endpoint that we can test out and take a look at. Have a good time with. Pass it pictures of me doing rock, paper, scissors. It should be done. It should be done soon. When did we do this command? Let's go back over here. It should be done like a minute before the show is over. If I did this right. Come on. If I did this right. Globetrotters tomorrow. That sounds awesome. AZ204, best of luck, my friend. Abhilash, you're going to do great. I feel it in my bones. Here we go. Come on, be done. 59. Push. Let me get my request open. This is a picture of me doing rock, by the way. You can do it. Refresh. You can do it. Oh, we're not going to make it. But if you want, I can show you another endpoint that does a similar thing. Let's test it. This one already we've done. This is what it's going to look like. Boom. Yeah, is that cool? Isn't that just beautiful? Look at that beautiful footage. Thank you so much, my friends. We will see you next time. Take care.